Yeah.
It should be ready to go.
I have your exams. I call me by last name alphabetically. Colin Berry, Jason Spiginowski, Lauren Gray, Brandon Kappa, Anil Clark. Aaron Cook, Taylor Davis, Aaron Quayle, Anthony Brian Goff, Madeline Blank. Jason Gority, Alex Graves, Leslie Groff, Andrea. Andrea, you can have Hopkins, Jake Hopkinson, Levi Yurgor, Morgan Clover, Jalen Lee, Brandon. David Norris, April, Reeves, Reed Randall, Maya Robinson, Reed Rodley. Nathan Sanchez, Ron Pierce, William Soto, Cameron Scrub, Benjamin. John Woods, Daniel Warner, Jeffrey Wells, John Wall. Yeah. Samuel Decker. That's distribution. This should be the total green. Remember, there is a curve from not just from here to there. You go from here to the total first, and then total to there. There is a curve. I have returned back 20% of all the points that you have lost for the whole. Until now, whatever you have lost, 20% has been. But if this number changes, keep changing your number. So make sure you make your judgment appropriate terms. And what else? That's what it is. Yeah, I should have graded before I wanted to, but I apologize for that. But 1 week, it's not that bad. Any other comments on the exam?
Is the curve already applied on D2L?
Yes, the curve is applied. This is after the curve. And I think on D2L, how you see it is, there is a final adjusted grade that is manually done by me, that is not automated. And then there is a final calculated grade. I think this is what happens on the student side. So the final calculated grade changes every time there is an update on the D2L. For example, if one of the graders updates the next homework, it will automatically do it. Even if any change on the D2L, it updates it automatically. The final adjusted grade is manually done by me. I go and manually change that. So that I accommodate this. So what I do is I take the final calculated grade and add 20% to that. Or I shouldn't say that. What I do is I do one more thing is that the exams are out of 45 at this moment, and the final exam is 0 grade. So I put the average of all the midterm exams into the final exam, so that it's a better representation. Otherwise, it's a little diluted grade because the homework is weighted more, or homework is easier to score. So if I were to not do that, it might be a little diluted grade. So your grade goes down a little, and then I curve it back up. So eventually you get a reasonable amount. So that's how I do that. If there is any confusion on that, feel free to ask me, or do you have any questions at this point? Yes, please.
Can we go over
Number 5. They remind me about it?
It's the one with the 4 identical model parts.
Oh, yeah. So there are 4 charges. There's positive charge, let's say that's positive charge. That's positive, that's positive. They're all are charged Q. So that's 1, 2, 3, 4. And all of them are charged Q. So that's, I think this was point A. That is point B. Let's say that's length L of the site. And the potential at point A is very easy. So you can calculate, so it is take Q over, if this is L, this is square root of 2 times L, the diagonal, full diagonal. But it's only half the diagonal, so it is square root of 2 times L divided by 2. It is nothing but L over root 2. And there are 4 pieces like that. That's take Q over root 2 L over 2 plus take Q basically 4 times that, 4 of that. And VB similarly is equal to, from here, it's only L by 2. So that's take Q over L by 2. This is also the same, but take Q over L over 2. The next one is the distance from the point 3 or point 4 that comes into picture. This is L over 2, that's L squared plus L squared over 4, that's 5 over 4. So that's take Q over square root of 5 over 4 times L plus take Q over square root of 5 over 4 times L. And the idea is to subtract this out. So V minus VA or V, right? Whether you did A minus B or B minus A, I did not care, but actually the problem was asking between A and B. So it could be VA minus VB, but I was not particular about that. So take Q over L, and it says 4, I suppose. And that's 4 over square root of 5. These two. And that is a 4 root 2. And you can simplify this a little bit. Does that help? So that's all that was, oh, I shouldn't say that's all, because there are some distances involved, and a bit of work there. Okay. Any other comments or questions? That is a homework. 7. November. On Tuesday. Homework 8, you want to be careful. This is due on the day of the exam itself. But remember that Tuesday is the holiday. So this is due on the day of the exam. But what I have done is that there is a buffer on this, even if you are 24 hours late, you should be okay. So there is a good amount of buffer put on this, so you don't have to be very desperate about submitting the homework, but that doesn't also mean that you can take it, take too long. That is a, it should be safe for you to work on the exam first and then worry about the homework. That's what I mean.
The midterm 3s over homework 7 and 8.
Oh, no, midterm 3 would be 6, 7, and 8 because we did not really use 6 so much. So that's a good point. This will be homework 6, 7, and 8. So even though 6 appeared for midterm 2, also I first of all asked only one question on that, and it was clear to me that not, or it will be good to go over it again for midterm. Okay, good question. Yeah, thank you. We started talking about magnetic field, and we said any moving charge creates a magnetic field. You want to talk about generating magnetic field? The easiest way to create a magnetic field is to have a magnet, right? The refrigerator magnet that you have, around that there is a magnetic field. Whatever makes the other magnet or another iron object attract to it, that's what a magnetic field is. But we don't have too much control on that. That's a naturally occurring material. So you have to go sub and mine for it. But that's not what we would like to do. That is an easier, more controllable thing, and that is a current carrying wire or any moving charge creates a magnetic field. So moving charge which is Q times V, charge which is moving, right? That creates a magnetic field or a current carrying wire. Current carrying wire, and the wire itself need not be straight, so we talk about a differential current carrying wire, so that's I times dl, where L, the direction of the wire when you have a wire that is not really direct in the sense it could be, if you have a straight line, it could be to the right or to the left. So the direction of that wire is given by the direction of current. Direction determined by current. That's the two sources for the magnetic field. Both these both create magnetic field around. So first, let's talk about the magnetic field created by this tiny element of wire. So let's say that's your tiny element of wire. This could be the same idea with Q times B also. So this could be a piece that is a wire here in this form. Like this is a small element of the wire, and this is I, which is the direction of the current, and the DL is the length of the wire. And we would like to calculate the magnetic field somewhere around it, to create a magnetic field everywhere around it. If you think of a magnet, there is a magnetic field everywhere around. So that is an observation point you're picked. So let's say that's your observation point. And let's call that a distance R from the wire. So that's your observation point. So you have a current carrying wire, and somewhere a distance R, the vector distance R from that wire, that is an observation point, and you would like to know what is the magnetic field at that point. And it is given by, so this is what is called Biot-Savart law. Biot-Savart law tells you what exactly is this magnetic field. This is a tiny element, so we will say it creates a tiny differential magnetic field, infinitely small magnetic field, and we will add up. If there is a long wire, we have to add up all the differential elements to that, and that gives us the total magnetic field. So the tiny magnetic field that differential line element creates will be the differential magnetic field, and that's equal to, it is given in terms of the vacuum magnetic property of vacuum, that's mu naught over 4 pi times the current I times dl. Often we write dl as dr, so that's also one way of representing that. Cross vector, that's your vector product, R hat. Remember, whenever there is a hat, that means it's a unit vector. A vector hat, any vector hat is equal to the vector A divided by the magnitude of that vector. When I don't write the vector sign on it, that means it is the magnitude of the vector. So divide out the magnitude part of it, and that's the unit vector, or in better terms, it's a direction of that vector A. So R hat is the direction alone. Remove the magnitude part, and the direction alone is R hat. Divided by R cube, how far you're, or R square, how far you're from the from that current carrying wire. This is a cross product, so we should be able to use our right hand rule and get what exactly is the direction of that magnetic field. Use your right hand, point your 4 fingers in the direction of L, and that is a freedom around that direction, and fix that direction by pointing or letting this direction R to be facing in the direction of R. And then it is dismissed, it is still pointing in the direction of current, thumb is facing the R, and then you open your thumb, and you notice that the thumb is pointing into the board. So the magnetic field here will be going into the board. So that's into the board. I can change that observation point and can scan that observation point around. If I were here, that's magnetic field here, that's the magnetic field here. Everywhere on the right side, the magnetic field will be going into the board. Everywhere on the left side, when I'm on here, the observation point moves here, so that's here R. And now I do is that that's my direction of current. This time I will be pointing my palm towards the left side while I'm facing the board, and my thumb coming out here is coming out of the board. So that's the magnetic field everywhere onto the left of this piece. So in general, what happens is that, so this is something that you will see, is that if you have a current carrying wire I, the magnetic field will be given by, you can use this right hand rule, but that is a more convenient way. Just hold the magnetic field with your right hand such that the thumb is pointing in the direction of current. If you point the thumb in the direction of current, there is only one way of holding the current. There are two ways of holding the current, a wire like this or like this. And the direction of your fingers gives you the direction of the magnetic field. That means the magnetic field will be like this. They're circular around that wire. That's a three-dimensional view. Here, what we are saying is that the circular magnetic field on the right side, they're going into the page, and on the left side, they're coming out of the page. These are circular magnetic field lines which show up at 2 points, going in, coming out. But in particular, they look exactly like this. So let's make this better. If the current is coming out of the board, so this is I out of board. Now the point is that this same wire is coming out of the board so that I can see the circular feature clearly. And now I have again hold the wire. This is coming out of the board. Hold the wire so that the thumb is pointing in the direction of current, and the fingers gives you the direction of the magnetic field. So the magnetic field is like this. They're circular. And they get weaker as you go farther. That's your magnetic field. Notice the direction. This is counterclockwise, which is given by the right hand rule. This is sometimes called the right hand rule number 2 in your book and most of the places, but it is the same idea. It is coming exactly from the same cross product that we have. It's just a convenient way of remembering that every time you have a current carrying wire, if you are interested in finding out what is the magnetic field around it, just hold the wire with your right hand, and the curl of your fingers gives you the direction of the magnetic field. Notice that this gets more dense, the lines. Remember, the number of lines per unit volume is a measure of how intense the magnetic field is. Magnetic field is stronger, closer to the wire, 1 over r squared, 1 over r squared here. As you get closer and closer to the wire, the magnetic field gets larger and larger. This is coming out of the board. What about when it is going into the board? So if it is going into the board, so that's the same wire, but this time let's view it from the opposite side. So that's I into the board. Now you point your thumb in this direction, your fingers are going around that, so that's clockwise. So that's your magnetic field. It's weaker as you go farther. That's your magnetic field lines. As you go farther, the density is getting lower, and it is 1/r squared dependence in there. But we will notice that there is a, if it is a straight wire, if it is not infinitely tiny element of the wire, if we take a full wire, we'll notice that the dependence will change a little. So let's talk about, this is for a tiny element of the wire, like we had a point charge when we were talking about electric field, and you add up all the point charges to get different configurations. Here the configurations we'll talk about is a straight line, a wire of finite length and extending from certain point to another point, and circular wire. Those are the two configurations we'll be interested in. And one more, which will be called a solenoid, which will be a coil, but that will be just a uniform magnetic field, so that will be convenient. So let's consider a straight current carrying wire. And let's have this as our diagram. That's our straight current carrying wire. And let's start with a finite wire. But when these 2 points are taken away to plus and minus infinity, that becomes an infinite wire. And we will see that the expressions are significantly simpler for that infinite wire, just because these parameters involving the length does not come in. We need to specify our observation point, and that let's say somewhere here. That's your observation point. But that means that we are interested in what is the magnetic field at that observation point. Every point, every tiny element here will create a magnetic field going into the phase, right? Hold the wire and the fingers go in on the right side, this goes on the left, it comes out of the board. So everywhere it is going into the board. So let me say this is X, that's Y, and that's your Z. So that going into the board means minus Z hat. So minus Z hat is, so that's Z, so minus Z hat will be into the board. Into board. So it's just a reference so that whenever I write minus Z hat, it means it is going into the board. It's even better to, instead of saying it is minus Z hat, because minus Z hat is only at this point, right? When it comes here, it is actually plus Z hat. So the best way to represent that direction of the magnetic field is that it is tangential to the circle. So often we will use the direction, so let me write that here. So the letter phi hat will mean tangential to a circle. We can make it better circle about its symmetry axis. It's think of symmetry axis as the Z axis in this case, or in this case, the wire, right? That's your axis that is formed. And you're talking about a circle, have a circle around it, and the tangent to that circle will be represented by phi hat. That's much better That's saying it is minus z hat, because minus z hat is only true at this particular point based on my coordinate source. Okay. We will notice that this mostly depends on the distance, how far you're from the wire, and let's call that rho. So that's rho, the Greek letter rho. And since we know what's the contribution from a tiny element, so let's say that's your tiny element dl, and that's your observation point from there. So I know the contribution from this point, and I'm going to add up each of these contributions from this point to that point. Okay, so that's going to be our strategy. So the total magnetic field, or first let me write EB is equal to mu naught over, I need to first write the okay. So mu naught over 4 pi times I times dl crossed with r hat over r square. Instead of writing r hat over r square, what did it say? Yeah, it's fine. That's r square times r hat. So that's exactly the same expression that I wrote here. I just rewrote it in that place. The L is nothing but it is in the direction of y hat. So the total magnetic field will be integral of this going from the bottom point to the top point. I have to keep adding them. So I integrate on this. That's mu naught over 4 pi I. I have a distance r here, so that's my distance r. And let me say this is a length y here. Your y, and let's say that's current I that is way. Y and the rho connects me with r, so that's y square plus rho square. What's in the denominator? Y square plus rho square. dl crossed with r is nothing but the dl itself. R hat as a unit vector, that's 1. So that's dl times sine theta. Sine of the angle between these two quantities. Let me specify this angle by angle theta here. But I'm interested in dl crossed with r hat, that's down here. So that's sine of 90 minus theta. And that's because cross product A cross B is AB sine theta. A is the length of the first vector, that's BL. The length of the second vector is the unit vector, so it's 1 times sine of 90 minus theta, because I chose to use this as my reference angle instead of this. This is the angle that contributes to the cross product. So it is sine of 90 minus theta. DL here is nothing but dy, right? So I will replace dl with dy. It is a tiny element along the y-axis. So it's just dy. Sine of 90 minus theta is cosine of theta, and cosine of theta is rho over r. So cosine theta is the adjacent angle rho over the hypotenuse, which is r, which is y square plus rho square. Cosine theta is sine of 90 minus theta. Put this in here. So that gives me mu naught I over 4 pi, which is a constant that can come out, dy. There is a rho in here, and divided by y square plus rho square 3/2. Two lengths from here and one length from here, so that's 3/2 of that quantity. Again, what are we doing? We're just adding up all these contributions. This integral is easily doable because you're integrating on y. You're integrating from a lower point in y here to a extreme end on that side. And a substitution that is convenient for that is y is equal to rho times tangent theta. Y over rho is tangent theta, geometrically also true, but this is just a integral substitution, but geometrically it's clear what is happening. You would like to go from an angle theta 1 here to angle theta 2 all the way to the top. If y is rho tangent theta, dy, this is what we need here, is equal to rho secant square theta times d theta. Substitute that in here, y square plus rho square, that is again secant square theta. So y square plus rho square is tangent square 1 plus tangent square theta is secant square, so that's rho square secant square theta. Put that all together and we learn that it is mu naught I over 4 pi. That is the rho in the numerator, and integrated dy is rho secant square theta d theta, and the denominator we have secant cube theta, and that is a rho cube. That's a simplification. 2 rows in the numerator, rho cube in the denominator, and secant square cancels out. Whatever is left is 1 over secant theta, and 1 over secant theta is nothing but cosine theta. So we get a simple integral here. That's mu naught times I over 4 pi and 1 over rho, and an integral of cosine theta, which is sine theta. But you would like to go from a bottom point to the top point, so you are evaluate this from theta 1 to theta 2. And theta 1 and theta 2, so let's see what that result is. That's what you want to keep in mind. Magnetic field due to a finite wire, finite straight wire, and again that's the diagram. So this time I'll show only the relevant parameters. And that's your observation point. That's observation points. The length or the distance, how far is the observation point from the wire? That should be 90 degrees. Okay. And notice this observation point need not be exactly at the midpoint. I've chosen it purposely somewhere symmetrically. In fact, this could even be somewhere here. It need not be within the wire at all. It could be outside the wire, anywhere in principle, except it is not really on the wire itself, because that will blow up there. We would like to represent this line instead of by L1 and L2, instead by this angle. How long is this wire? that can be described by angle theta 1. If I give you angle theta 1 and this distance rho, you actually know the length L1. So L1, so rho over L1 will be sine theta 1. So let's say L rho over L1. So it's L1 is tangent theta 1. And that's this length you want. So that's L1 and that's L2. But that's just an added information. It's only sufficient to write in terms of angle theta 1. And then here, that's angle theta 2. So that's your information. That's a way of providing what's the length of the wires. And the magnetic field due to this wire is equal to the right hand rule gives you the direction, which is tangential. It is circular around this wire and it is tangential to the circle. And there is mu naught over 4 pi, it always shows up. It's like 1 over 4 pi epsilon naught in the case of electric field. And there is I over the distance rho. And you have sine theta 1, sine theta 2 minus of sine theta 1. If I write it like this, that means 1, so this is the positive direction. So this way, theta 1 and theta 2 are positive when it is clockwise. I can also write this as, sometimes you will see in your equation sheets, sometimes it is written also as sine of theta 2 plus sine of theta 1. And if that's the case, you say theta 1 is positive counterclockwise. And theta 2 is positive clockwise. So basically, I have observed the direction in the, like I'm measuring theta 1 and theta 2 in different manner. And sometimes geometrically speaking, this is useful. But when you see that as an integral and you have a coordinate system, then that's how it shows up. Either way, make sure that you're aware of what is going on. That's for a finite wire. Remember, theta 1 measures you, gives you L1 here, and that's L2. One would immediately like to consider this equation. What about an infinite wire? And we would also like to talk about an off infinite, right? What if the wire ends exactly here, where the observation point goes in there? So infinite wire. If this wire is this point, let's say the reference point is A and that's point B. If my point A goes all the way to negative infinity, what can I say about the angle theta 1? If the point A goes all the way to negative infinity, what can I say about what can I say about angle theta 1? Pi by 2, like 90 degrees, right? And same thing here. So infinite wire in both extents will be given by theta 1 is equal to, let me say pi by 2, whichever, let's use pi by 2 counterclockwise. So this is counterclockwise, and theta 2 is equal to pi by 2 clockwise. And half infinite wire has this meter. Remember, if it is half infinite, it is necessary that the observation point is exactly at the center point, and here there is a reference line here, and in that sense, it is possible to talk about a half infinite wire. So that's your reference point. So on this side, point A goes all the way to minus infinity, and point B goes to 0 here. So theta 1 is pi by 2 counterclockwise, and theta 2 is equal to 0. So let's calculate the magnetic field for this. So that for infinite wire, you have magnetic field B is equal to, that's phi hat mu naught over 4 pi. That is the current I and the distance rho all intact. But now this is pi by 2. Right? If you are doing counterclockwise and clockwise, I can use the second expression. So it is sine of pi by 2, which is 1. Sine of theta 1 is also sine of pi by 2, which is 1. 1 plus 1, that's 2. So that's 1 plus 1. So often you will say this is 2I over rho. That's how it will show. What if it is half infinite? Then you again say that's phi hat mu naught over 4 pi I over rho, and this is 1 plus 0. Theta 2 is 0, so that's theta 2 is 0 plus 1, which is basically just 1, and you can ignore that parenthesis. Often these expressions are very handy, and most of the time when there are problems in your exams, they exploit these expressions a lot more than the integrals and other derivations. So make sure you have a clear picture of what's the direction of this magnetic field, how do they look like. They are circular around the current carrying wire, and it is 1 over rho dependent, like your point charge, which was 1 over distance square dependent. This is 1 over rho dependent and proportional to current. So what creates magnetic field for a sufficiently long wire is the current I. It is proportional to current I, and it is inversely proportional to the distance. The direction it is circular around that wire. That's the free information. And mu naught here is a constant permeability of vacuum. So this is called the permeability of vacuum, or you can just say magnetic property of vacuum. This is more technical term. This is how you can imagine it to be. And it is equal to, then the 4 pi in it, which cancels out that denominator exactly. So 4 pi into 10 raised to minus 7. And the unit is Tesla meter over amp. Ampere is the unit of current. And we already talked about this number last time, that the electric property of the vacuum and the magnetic property of the vacuum, then you multiply it, then you take the inverse. Remarkably, you get the speed of light in vacuum. Like light, which is, we never expected to have any electric or magnetic properties at all, is actually an output coming from these considerations, which we will see later. So that's a wire, but now I said there are two configurations that are important. One is a wire, a straight current carrying wire, exactly like it shows here, and also a circular wire plays an important role. So let's think of a circular wire now. the circular wire. In fact, it doesn't even have to be a circular wire, it can be part of a circle, and even that would be okay. But there is one catch with this configuration, notice when we were doing a straight wire, we could keep our observation point wherever we want. And we could actually get an expression for the magnetic field. But for a circular wire, we are limited. We don't have the abilities in principle. If you do a little bit more of mathematics, it is possible to write your magnetic field in terms of what is called elliptic integrals. But those are functions like sine functions, trigonometric functions, but you haven't come across that in your mathematics courses yet. So we will have to, because of that limitation that we haven't studied sufficient mathematics here, we will limit our analysis only on the axis, in fact, only on the center of the circular wire. It can be done on the axis also very easily, but here I will limit it to the center of the circle. So the observation point at the center on the axis or center. One can do this for the axis, but here I'm simplifying it more and saying it is exactly on the center. So that's your observation point. Observation point. Maybe you write that as P. P. T is observation point. And we have a circle, but this is only part of a circle. The wire actually is only constituting an arc of a circle, and that's the current I that is going to. And we would like to specify this arc, and the arc is conveniently specified by the angle it subtends at the center. What's the radius of the circle? Let's say that's r, and angle, let's call it alpha. Alpha. Okay. We know we would like to notice we are trying to get the magnetic field at the center, right? Not anywhere else. In principle, one would like to have the magnetic field here also, but that's harder. It can be done, but not in this code. What will be the direction of the magnetic field down here? Let's begin with that. We hold the wire, right? Every point of this at the center, we hold the wire in such a way that the thumb is pointing in the direction of the current, and the curl of the fingers at this point gives you the direction of the magnetic field. But you hold this, notice that the fingers seem to be coming out of the board here when you hold it. So that's coming out of the board. So the magnetic field B comes out of the board, comes out at point P. Only at point P. Everywhere outside the circle, it will be going in. Everywhere inside, it will be coming out of the board. So let me say V hat is in that direction. That's fine. V hat, and then I have my magnetic field. You would do a tiny element, which is mu naught over 4 pi times I times VL. That's my tiny VL here. VL. That's in the direction of the tangent to the circle. Cross with path divided by how far you are from the observation point. But this is a circle, so that's very convenient because that's the same distance. Every point on the wire is exactly the same distance from the observation point because the observation point is in the center. That's the simplicity involved with being at the center. So that's R square. DL cross with R, we already argued that that's coming out of the board. So I only need to write this as, so this is mu naught over 4 pi and I over R squared. DL and R hat is the radial vector, DL is the tangent vector. So sine of 90 comes in, that's sine of the angle between them is 90. So DL, which is R times d theta. So I've used the idea that DL is R times d theta. That's your R. Right? That's your distance, radius times the angle. It gives you the R point. Times 1 times sine of 90 degrees. And that's divided by R squared. If you are integrating this, and the direction, right? That's the z hat. If you integrate this, we have z hat comes out, mu naught I over 4 pi R, and I have to integrate it is d theta. If I integrate by angle theta, that will be alpha, the total angle will be just alpha. So that's equal to z hat times mu naught I over 4 pi R times alpha. If I have a part of a circle, so that's your alpha, and immediately you can think of complete circle. So if you have a complete circle, my magnetic field will be B will be z hat times mu naught I over 4 pi R times, for a complete circle, alpha is 2 pi. If it is a half circle, B will be equal to z hat times mu naught I over 4 pi R times pi. That's half a circle. If it's a quarter circle, get the pattern now. You can do this for any arc length, right? Alpha is just from special cases I'm giving, which probably is illustrated. Mu naught I over 4 pi R times 2 pi, so this is pi over 2. And that should illustrate how you work with circular wires and straight current carrying wires. With these two, now we can build slightly more complicated configurations. Let's do a few examples here. And your homework has this example showing up. So let's say we have example. So let's say we have a current carrying wire coming this way. It comes all the way from minus infinity, and this is the point where you would like to measure better. Let's just say that's your observation point P, and the wire itself goes straight on that side. If current I and the same current goes through here. This forms a circular wire, so that's your A, that's your length A. And P is your observation point. we would like to calculate what is the current at point P. We say that this wire, as far as P goes, the first wire starting from point this to point A, that's a half infinite wire. This is a quarter circle, and that's another half infinite wire. And we just have to worry about the directions after that. Are they all adding up, or are some of them adding and some of them subtracting? So as far as we take care of the directions and we break this into 3 pieces, we can use the configuration that we have pretty. So that's 1, 2, and 3. All of them have the magnetic field going into the board at point P, right? From 1 it is going in, from 2 it is going in, from 3 it is also going in. So first argue that all 3 are going into the board. That we have is going into the board. And the magnetic field then is equal to V1 plus V2 plus V3. That's equal to V1 will be V hat times mu naught times I over 4 pi. So we had half, but the half infinite wire, there was a half infinite was this down here. So we have mu naught over 4 pi times I over A, because A is the distance now, and you have 1, right? 0 plus 1. So that's all that is to it. Plus V2 is V hat times mu naught over 4 pi, and it's quarter circle. We said for a quarter circle, it is I over R and then pi by 2. But I over A this time, and then that is pi by 2. And the other part is again and half infinite wire. So that's plus V hat mu naught over 4 pi times I over A. That's coming from this. We can put this all together. That's V hat mu naught over 4 pi times I over A, and that's 1 plus pi by 2 plus 1. So it's 2 plus pi by 2. Let's, for completeness, let's put in some numbers. We have, let's say I is equal to 1.0 amp, 1 amperes, and A, let's say, is 15 centimeters. So this will be what we have times mu naught is 4 pi into 10 raised to minus 7 divided by 4 pi. 4 pi conveniently cancels out. Let's say this is 1.5. That will cancel out then, so that will be here. So that's 1.5 amp divided by 0.15 meters. And we have 2 plus pi by 2, 2 plus pi by 2. That's equal to we have times so pi by 2. That's 3.6 into 10 raised to minus 6 Tesla. Notice this is the 1 amp of current that is sufficiently strong, and the magnetic field due to Earth, when we are standing here, that's about 10 raised to minus 4. So this is about 100 times smaller than that. So one would think that currents do not produce significant, but you can put multiple wires, right? So typically the idea is that you wind your wires in such a way that you have hundreds of them. Like you have 100 wires together as a coil, And then you immediately amplify this by 100, so you can easily multiply this magnetic field significantly very easily. I can stop here, so for a change, I should stop 5 minutes early. And next time, we will talk about Ampere's law and the forces between wires. Thank you.